Welcome, everybody. I'm one of the many ACM volunteers. My name is Greg Makowski. I've been inviting data science speakers since 2008. Tonight's talk is LLM Graph Database for Retrieval Augmented Generation, or RAG. So we've got two speakers tonight, Soham Dhodapkar, a solution engineer, and Andreas Kollegger. Background about our ACM, our local chapter. How many have been to our events before? Let me turn it around. How many is this their first time at SFA ACM? Oh, wonderful. So did you find us on Meetup? Okay, anybody find us some other medium, either word of mouth or go ahead and shout it out? Yes? Word of mouth? Okay. Oh, email, okay. Did anybody see this in the BitDropper or paper newsletter? Okay, sounds good. So a little bit about our chapter. So the ACM.org, the headquarters is in New York. It's the Professional Society for Computer Science for a lot of computer science departments and universities. They have a lot of the journals and conferences and publications. What we are is a local regional chapter, as opposed to a student chapter at a university or a regional professional chapter. We were founded in 1957. Our focus is promote knowledge of modern computing. We're a nonprofit. We want to create community, support networking and hiring, $20 annual membership. You can see our upcoming talks on our Meetup site and our historic 200 plus talks of our more recent talks on our YouTube channel. In general, we shoot for 2 monthly meetings, a general computing meeting on the 3rd Wednesday of the month and a data science meeting on the 4th Monday of the month. Let's see, sometimes we do joint with other groups. Some upcoming events, we have a color code. There's a SIG graph for graphics on Thursday, January 25th, immersive media, streamlining the path to mainstream consumption. And then on Wednesday, February 1st, there's a round table taking generative AI enterprise models to production. So that's part of a AI user conference, 3-day user conference. That's coming up. That's a Monday, Tuesday, Wednesday. So I believe our talk is on the Wednesday on the developer day. On Tuesday, February 20th, there's a Engineers Week banquet and Hall of Fame ceremony. On Wednesday, March 27th, there's a computational medical discourse by Boris Galitsky. So he's been doing NLP for about 20 years, has a large number of publications and patents. Also in mid-March, there's a Synopsys Science Fair. So this is something where we are looking for volunteer judges, such as you from the audience. We need to cover maybe 1,000 middle school and high school projects. We want to support STEM, science, technology, the math and engineering. And so this is to judge the science fair projects for middle schoolers and high schoolers. And so we would, in the past, have given a 1st, 2nd, 3rd grade project award, and then also award to the teacher to try and encourage computing. So it doesn't have to be data science, to be any form of computing. But the reason we have to review all of the projects is a project may declare themselves as physics or biology, but they may still have a computing component in it that's significant. So that's why we try and review all the projects. And there is no category they have for just computing. So we are looking for that. If you are interested in coming on a Wednesday, helping go through that, we do a first pass through all of them, find out what's a good candidate, and then we do a second pass. So talk to any of the ACM volunteers. ACM volunteers, raise your hand. Bill is one, I'm one. Yasha was up here, was one. There was a number in the lobby. So we can also use chat in Zoom. I believe Yash will be set up with that. If there's questions for remote people to the speaker. And then also call for volunteers. So we're a nonprofit. So there's a variety of things that people can help with: online membership, publicity, marketing. We might look for other facilities besides Hacker Dojo that are bigger. We can make use of this, but Neo4j was a good sponsor and covered with a security cost tonight. Not something that we can do every time. So we also like to network for people that might be employees of big companies that could rent out an auditorium or reserve it for a nonprofit. Okay, so just to introduce the talk tonight. So on the subject, LLMs may sound frequently like a know-it-all, quickly responding with a plausible answer, but that could be a fabrication. So we can ground LLMs in reality using a knowledge graph. So tonight's talk will show the benefits of a graph database over a regular database. It'll show how to use RAG to reduce hallucinations, enforce security, and improve accuracy. Discuss the advantages of the vector index plus the knowledge graph, and they're going to demo an end-to-end retrieval pipeline in a Jupyter notebook. So there's a GitHub for Neo4j and their Neo4j's website. Also, I asked the speakers in the meetup site, if you scroll down to the bottom after the posting of the talk description, there's a comment section. So anybody can post comments there. I invited the speakers to post a link to a PDF of their slides, because sometimes people like to take pictures of slides or follow up. And then also I asked them to do a post of the GitHub, because tonight's demo had a demo out of a GitHub. To introduce the people, Soham is a solution engineer helping users all over the world. He's an AI and data science enthusiast with a research experience. Andreas is a technological humanist. At NASA, he designed systems from scratch to support science missions. In Zambia, he built medical informatics systems. At Neo4j, he's been democratizing graph database to extend our intuitions of how the world works. So please have a warm applause for our speakers.
Thank you, everybody. Thank you, Brian. Is that too echoey? How does that sound out there? Sounds okay. Okay, thumbs up. And hello, everybody out who's dialing in for today. I feel like I'm towering above you. I don't know if you can tell. Let's see a little video right there. So hello, I'm Andreas Kollegger from Neo4j, as Greg introduced, and thank you again all for joining us today. We're going to talk about knowledge graphs and LLMs and how to bring all these things together, do some fun things. I'm going to start. Oh, now our talk will begin. Thank you, FFAACN. Really appreciate it. And I've gotten out of the slides.
Well, thank you, Neo4j, for sponsoring the tonight.
Oh yeah, thank you, Neo4j. Okay, hello again. So we'll get started again on this part of the talk. The GenAI stack. So what was it, about 2 or 3 months ago now? So Neo4j put together something with our friends at Docker and some other folks, a nice little stack for how you can assemble a GenAI application. That's going to be part of the talk today, is we're going to look at that, and then how you can actually think about building applications on that. Okay. Generative AI. Aside from memes like how do you fix a computer by, just power cycling or unplugging and plugging things back in again, there are also, of course, lots of memes around generative AI and what it really is. Surely you've all seen at least this one, that generative AI is a parrot. Comes around, like you'll see TikToks about this, every now and again. Another one that I think is kind of fun is that generative AI is just a sock puppet. So if a parrot is just some other thing that is imitating, people language, sock puppet is actually you talking to yourself, and which that really happens when you talk to ChatGPT. It's just really trying to be pleasant for you, and that actually means that it's trying to imitate you as much as it can. This is the meme I think that is most useful if you're thinking about working with ChatGPT or any kind of LLM and building applications with it. Thinking about it as if it is not a parrot or sock puppet, but it's alien technology that you're trying to interface with. We've all seen the sci-fi movies where some alien power source or some alien something or other somehow becomes into our possession, and somehow humans figure out that even though this thing is like doing some kind of crazy physics or who knows what it's actually doing, we somehow figure out how to plug into it and then take advantage of this alien power source, right? So if we think of AI in that same way, it's actually not a bad starting point for thinking about how to do the integrations with AI. And the challenge then is, okay, how do you go from all the human technology we have to this alien technology? How do we plug these things together to get them to work together and do useful things? So through these memes, there's a couple of things that come up that are challenges with AI, and that this last meme, the alien technology, tries to address a little bit. So the memes like, okay, if it's a sock puppet or if it's a parrot that is really just mimicking either you or the crowd of the world, where it's actually drawn its inspiration from, where its knowledge actually comes from. So if you're talking to ChatGPT, you might get answers that are actually ultimately coming from Reddit, which we all know is a great source of truth. And maybe some, positive attitudes as well. Very joyful place to be, right? So all these things influence what the LLM actually knows about, how it, speaks, how it interacts, how it behaves. And so you have to be conscious of that when you're dealing with it, right? Like it's possibly like wading into any kind of random subreddit and just sort of asking it a question. You might get some helpful things, you may not get some helpful things, you might get people just complaining at you. There's a lot of techniques that people actually have in place for how to guide that, but it's a challenge, just actually getting the LLM to do useful things, because it's just trained on a bunch of public information, which may or may not be the best quality for what you're trying to do. It also has challenges where, like, aside from just, quoting subreddits, that it just kind of makes stuff up because it is ultimately just a prediction machine. It is really just autocomplete on steroids is one way to think about it. And when it's just kind of trying to autocomplete, like given the text you've put in, how do you continue that text? It seems like it's a question and answer, but from the LLM's perspective, it is just, you've given it a stream of text, or you're just asking it to continue that text. If you've ended your text with a question mark, then the way to continue that is to maybe respond to that question mark. Oh, you've asked it a question, it'll continue to come up with text. It seems like it would be fulfilling the first bit of text, which happens to have been a question. So the answer might be an answer, the continuation might be an answer. But that's really what's happening, is it's really just continuing text that has preceded the chance you've given it to actually respond. One other challenge that comes along the way here is that the text that it is generating, because it's just kind of making stuff up, it may not actually be relevant to what you're asking. It might be completely fabricated, or it might be unhelpful. It does its best to try to help it. There are lots of techniques for how people try to then game the system a little bit. There's this entire idea of prompt engineering. And prompt engineering as a thing has come up just because it's hard to get LLMs sometimes to do the right thing. Over time, that improves as the system learns what people actually mean when they ask stuff. If you've dealt with Alexa or Siri or any of those kinds of devices, they're really good at setting timers, for instance, because most people just ask those things to set timers. And so like all the variations on how to set a timer, really good at that. Things that are outside of like what it's normally used to, it's not necessarily as good at. These are all challenges. Another area of challenge ends up being, if it is just all these LLMs have been trained on public data, but you have a bunch of information that is useful that is not public data, but you'd love to be able to access it in that same kind of natural language way, how do you connect things together? That, of course, is the context that we're dealing with today and the meat of the talk, really. Okay, so let's deal with this last part here, is limited to public knowledge. How do we actually bridge that gap so that there's private knowledge that's available to the LLM, that the LLM won't make up answers around, that when you actually need a real answer, comes from what you know are facts, because they're stored somewhere that you trust. You just want the LLM to be able to, know that, understand that, and actually give that to people who don't want to dig into the data directly. So here's our challenge. We've got alien technology. We've got humans that want to interact with it. Let's try to bridge that gap. We'll try to integrate with the alien technology. And actually, this is
if you don't mind, just keep this to the side in case there's any questions.
Okay. Yeah. The good news for those of you who are following along remotely, all these slides will be available online, and I'm happy to visit you wherever you are and give you a one-on-one, talk through this stuff if you'd like to. So don't worry, all is not lost. We're talking through the GenAI stack. We've gone from the top layer, the application layer, down to here at this point. You've got to pick a database. So we've got the application layer, you've got a LLM somewhere, whether that's running locally on your laptop or you're using OpenAI or one of the many services that are available out on the web, or move the floating bar. Wait, what do you want?
Go to more.
Go to more. Yeah. I will briefly click that.
Then escapes.
I see. Okay. So what's happening right now is that the same way that you would train an LLM, I'm being trained on how to use this system. And by the end of this, hopefully I'll be completely trained. I'll be able to actually do this fluently. So we had application layer orchestrations, frameworks for actually integrating with your application and an LLM, whether it's running locally or in the cloud, and then a database, and ultimately past the database, so if I can still click forward. Then also files still exist in most of our applications as well, because files are where things start, particularly if you're exchanging information between different systems. Files, whether they're source data themselves or they're intermediary representations of data, they're always around. So CSV files, JSON files, or raw files like PDFs, all part of a GenAI application typically these days. Okay, so that's the GenAI stack, a quick tour through that. We're gonna get on to the fun parts here. If you've got all those components together, the behavior of those things in an application ends up being you have an LLM that you're using for a language interface. Some user somewhere is typing something in, and in a pure GenAI application, pure LLM application, you're just taking the user input, sending it to the LLM. The LLM's like, that's interesting. Let me see what might come next after the text that the user entered in. It is just a continuation of that text, right? Could be a Q&A, could be whatever you happen to type in. If you want to do more than that, if you want to take advantage of this stack, there's a pattern called RAG, which is Retrieval Augmented Generation. And so the generation part is because it's still text generation. You're helping the LLM generate some text. You're going to augment the context of the conversation that's happening by doing a retrieval first. So working backwards from the G to the A to the R. We're going to retrieve some information to figure out a better context for the answers you want to provide, and then augment the context that the LLM knows about. So they have general purpose knowledge. You can provide some specific knowledge to them in a context, pack all that up into like what would have been a very laborious thing for a user to do by hand. So you can go straight to an LLM and just type all this stuff in, like, here's all the context you need to know for giving me an answer, and then ask the LLM to give you an answer. Retrieval Augmented Generation, or RAG, is a application integration framework for doing exactly that, but rather than you typing everything in, you're going to reach out to a database, get some extra context, pack that all up into text, feed that to the LLM, and then let the LLM come up with an answer. Does that make sense? That's the basics of RAG. Okay. So, a generative AI app uses an LLM to provide answers. That's what we were just describing. With RAG, we're going to augment what's possible through the LLM. We're going to extend its knowledge to having access to a private database that only we have access to, giving it further context to generate answers. There are 3 scenarios to think about when you're doing this, and that's what we're going to talk about here. The classic place where people start with chat applications is they realize, okay, if LLMs are good with language, we've got piles of like files sitting around with PDFs, pure text, whatever it might be. Maybe it's customer support, conversations, things like that, user manuals, bodies of text that have really useful information that we generally don't do a lot with. We kind of just provide those, like maybe you can look through a catalog, pick a document, and actually read it. But now with an LLM, because they have such great language skills, pure text is one of the places where people start with chat applications, because you think, okay, great, let's take all these text files that we've got lying around, make those available to the LLM, and so that the LLM can provide direct answers to questions that people might have. So rather than the user saying, I've got a question about how to repair my refrigerator, trying to find the right model, trying to figure out what you might need to do to repair the refrigerator, you just talk to ChatGPT or talk to some sort of a chat interface that has access to all the user manuals, and then just let that happen by the LLM actually reducing all of the summary of information that it knows to an answer that you want to provide to the user for their specific problem. So pure text is a great place to start. If you have pure text, but then you also know a little bit about that pure text, like you might know that, in addition to the kind of description of like, let's stick with the refrigerator for now, not just that you have the refrigerator manual, but you know for sure what the model is, what year it was produced, what electrical requirements it might have, all those kinds of things. That doesn't need to be something that the LLM itself needs to figure out. You can just save that as metadata about the text, right? So you can extract things around that. That puts you into a scenario we have pure text mixed in with some data that you know about that text. And then the third scenario is when you don't have text, but you just have a database or a data lake or any kind of a warehouse of data, anything you might be storing data in. But you want the LLM to be able to give access to users to that without having to write SQL queries or anything else to actually get access to the data. This has a very different approach than the first two, but it's something that's still possible within this RAG framework. The key through all of this stuff, and the one kind of gap, I guess, that you'll see, is that the fundamental way that you interact with an LLM is through text. Either you have pure text, it's great at language, so that makes great sense, that's a good match. In the middle scenario, when you have a mix of text and data, you still have some text to anchor onto, so that's a perfect match for LLMs. It's that third one that's a bit of a question mark because, okay, you don't have any text, so how does that work? Somehow, if you want to talk to the LLM at all, you need to actually provide it some text. So how do you do that? So even on the third one, even though there's not text there, you have to figure out how to create text, how to create language, so that the LLM can actually do some interfacing and actually do some understanding of what's going on. Okay, so fundamentally, text is the coupling between the alien technology and the human technology, between us humans and how we think about things and what the LLMs can do. And even with our software, we've got to find our way to get some text so that you can give it to the LLM so that it can do something with it, right? So that's the coupling. We're going to start backwards from the hardest case, which is, okay, we don't have any text, so now what do we do? In the pure data retrieval bucket. I'll walk through this diagram and we'll spend some time on this before going to the other diagrams. In the pure data retrieval, oh yeah. Okay. I feel nervous now whenever I touch any window that's not, oh, let's see. Okay. Okay, so working around through this data flow here, and it's spelled out here, so I'm just going to basically be reading the bullet points, which is the best way to present any kind of information. It always starts with a user at a keyboard who wants to know something. So there's always what's called a prompt. The prompt is just somebody, who has a question, who has something they want to know about, and somewhere there's an end user who's typing in some text and hitting return, saying, "Hey, give me the answer to this." In this particular scenario, when we have the augmentation of the LLM is not some text that we have, but some database that we have, then what do you do for actually taking that user question and turning it into a question that you can answer from the database? That second part that is the tricky part. You've got text from the user, that's awesome, the LLM knows what to do with that. But before you give it to the LLM, you're going to say, okay, let me take that and figure out how to turn that into a question that we can answer from the database. So for most databases, what you end up doing here is you try to figure out if you can get a fine-tuned LLM, so not the one that's going to be talking to the user and providing kind of text and generating text, but one that's really good at generating queries, database queries. So you're taking the user's input and you're trying to turn that into a database query. So whether that's SQL or it's our beloved language called Cypher, which is a graph query language, or any other database that you might have, you can give the LLM access to that by trying to turn the user question into a query that you can run on the database, getting the answer back from that, then packaging all that up as text that you then pass to the LLM. The LLM then takes the original question, the answers that came back, and tries to generate an answer ultimately for the user. So you're providing context for an answer that has been drawn directly from the database. Now you can imagine that one of the challenges here is that it's easy to go beyond the complexity of what you think is easy to express in natural language. If any of you have ever had somebody who wants access to a giant, data warehouse that has some questions they want to ask of that, they'll turn to their data engineering team or their data scientist and say, "Hey, figure out some business insights for me here." They're not going to write the SQL. They're going to just describe to you what you want, and you have a bit of a dialogue with them, saying like, well, "What do you mean exactly here?" Like, there's nuances like, how do you want the results to be grouped, perhaps? Do you want like complete global scope? Do you want this narrowed between regions? Lots of follow-up questions before you can figure out how to answer a particular question that at the outset might seem easy to an executive, let's say, right? The LLM has that same challenge. People will start with like what seems to them pretty obvious questions to ask, but if you're going to generate a query from that, there may not be enough information from the original question from the user. So the naive approach is to start with like directly mapping whatever the user has asked, see if you can generate a query. That might work if people ask simple things like, how many chairs are in this auditorium? That maps super well to most query languages. You can figure out what that is do the mapping, run the query, get the answer back, provide it to the LLM, no problem whatsoever. The more complex you get, like just, how many chairs are there? Well, what do you mean? There's not enough information. Now you need to identify that there's not enough information to provide an answer. You have to have some follow-ups. So the first step here is pretty easy, but limited in scope to what it's able to do, because you might need more context. As the queries become more complicated, like, how many chairs are here that people are sitting in? Okay, now there's a lot more you need to know. You can start to add on lots of complexity that's hard to translate automatically. Even if you have a very well fine-tuned LLM that knows how to generate the query language, getting the mapping from the natural language to the query is non-trivial. So this is an area of active research for, I think, pretty much all database vendors at this point, including us for J. And we're going to improve how you can generate those queries, but then also this pattern of how you interact with the user to improve our ability to answer their question with a query. Does that all make sense? Okay, so I'm going to now put that aside because that's an area of ongoing research and random clicking. So the challenges here, as I was mentioning, is the first step, just getting it to work at all, actually getting to generate a query is not easy in and of itself. There are lots of good examples for LLMs to be trained on and fine-tuned on. This will improve over time, but it's not, out of the box, just kind of magically going to work. Even just to get queries that are syntactically correct. Because of course we know that for any kind of query language, you've got to have exactly the right syntax first. The second challenge is, okay, great, you've written a syntactically correct query, but is it meaningful for what the user wanted? Okay, that's also not easy to do. The last bullet here is kind of both the fun one and also a scary one, is that if you imagine all the different ways of having SQL injection attacks, now you're going to go past that and be like, okay, never mind SQL injection. Now you're dealing with an LLM. Who knows how it might be able to accidentally or through malicious use intentionally cause all kinds of havoc. Because we're all first focused on just trying to get things to work at all. We start with the happy path, as always. We just try to get things to work. And then we worry about all the bad paths, about how people might abuse it, how things might go wrong. This is a very big challenge. Giving an LLM direct access to your database is not the first step you want to probably take. But it's something that if you need to take, it's worth trying to invest the time into and doing some work on. Okay, this is the happier, easier, safer place to start, which is if you have just pure text, whether it's a collection of PDFs or whatever it might be, doing the pure text retrieval. And so we'll talk through that. This is basically the same flow that we talked through before, but now instead of taking the user's prompt and trying to generate a query from that, like a SQL query or a Cypher query from that, we're going to take that text from the user and we're going to create an embedding from that. And everybody here knows what embeddings are, or do I need to digress for a moment? Embeddings. More or less, yes. Okay, so the idea of an embedding is that you're just going to calculate for a given piece of text. We're actually going to ask the LLM. Most LLMs have a way of actually turning that into what's called a vector, where a vector is just a collection of an array of floating point numbers. And the way to think about vectors is, if you haven't dealt with them before, is to think about, for me, color spaces are always the easy thing to fall back to. We all know RGB. It's the red, the green, and the blue components of a color space that's in the RGB color space. That's just a vector that says, okay, for this particular combination of numbers, it turns into red or blue or ink or whatever the shades of color might be. What's nice about the color space is that similar colors, of course, are within the vector space, within the coordinates you have. The numbers are very close by, right? So if you've got red, you change a color that's pure red, and you add a little bit of blue to it. The vector that is that pure red and the red with a little bit of blue is actually still pretty close to itself, or close to each other, right? So that means that they're very similar in the color space, and that's exactly the same thing that happens when you create an embedding out of text or images or audio or anything else you want to embed for the LLM to take advantage of. You take that, you come up with some consistent way of creating a mapping from the original data source into a vector space. Once you've got it in a vector space, a legitimate vector space ends up meaning that anything that's in the vector space that's similar to something else in the vector space is close by in terms of the numbers. Now, RGB has only got 3 numbers. In vector spaces, you end up with thousands of numbers that determine what the space looks like. But they're just coordinates, is another way to think about it. Okay, so that's what the embedding ends up looking like. You've got the text, you create an embedding out of that. And then from that embedding, because you've already done a bunch of pre-processing on like all these PDFs or whatever you might have, all you're doing with a vector search is saying, okay, for this text that I've got, that I've turned into a number, a collection of numbers, what are the numbers are nearby there? Those are very relevant then for the original question. Let's return those back to the LLM, say, hey, LLM, the answer to the question that was posed by the user is somewhere in. So look at that to produce an answer to continue what the user started. Right? Mostly nodding heads, makes sense? Okay, cool. So that's what basically ends up happening here. Take the data from the user, the prompt from the user, turn it into an embedding, perform a similarity search using the vector index or vector search on that, get the results back, pass it to the LM, get an answer to the user. To do this, there's a bunch of pre-processing that's required to actually get the text into the vector space. What ends up happening there is that you basically have a giant batch job that goes through all the possible files that you want to be able to access, chunks those up into little bits, because you don't want to provide a 30-page PDF. You want to provide like a paragraph of PDF, so that when a user asks a question, that the question is going to match that paragraph where the answer is, not the here's 20 pages where the answer might be. Want to narrow it down. So chunking is the process of trying to figure out what the right size of text is that is most likely going to correlate with what the user input might be, so that the similarity is there and that you can get some relevance. You have a question?
Yeah, quick question. So chunking as a hyperparameter is also very chunky. You have your page, something that you see a lot.
It is. This step is easy to describe, like, oh yeah, you just chunk things up. The reality is that, like, for the given text that you have, how you chunk up makes a big difference, and how the LLM does the embedding makes a big difference. So there's a bit of experimentation here based on like what the particular LLM you're using is, what the vector embedding that it generates looks like. This is where you spend a lot of time kind of with a small set of the data first. Before you go through like a million documents, you take a subset of that, try to figure out what a good chunking size is, and then kind of go forward with that. Yeah.
Like it's numeric, you basically the drop curves or whatever else it is. But in this case, do you take a small subset and then look at eval harness or some other quantitative measurement accuracy?
Yeah.
Repeat the questions for the report.
Oh, right. So this is a question really about doing evaluation along the way, right? Like, so if you're doing some chunking, and this is a great point. If you're chunking up your text, how do you decide what the right size is? Of course, you can kind of zoom in the loop, figure out, like, is the answer that you're getting back from the LLM based on the chunking you just decided, is that actually accurate or not? There are also some different evaluation frameworks that are emerging. Like RAGAS is one like that tries to figure out, like, for a given chunking that you've got, for a RAG system that you've set up, for arbitrary questions that can be asked of that, what are the quality of the answers you're getting back, or the answers getting better or worse? We don't offer something like that ourselves at Neo4j, but there are like frameworks out in the wild that are being used for that. Did you have a question? Yeah. Cool. Okay, I should do a time check as well. Actually, I'm going to try to just move through. So I just realized, like, what is our time frame? Do we have?
Yeah, actually, have a particular time we have to be out here. I think you actually have your time if you want us to be out.
By 9:15.
By 9:15. Okay.
That's everyone.
Okay. So I will try to go forward a little bit. So we've got time for a demo as well before lots of questions at the end, in addition to kind of as we go along through here. So some of the challenges with just this chunking technique. So chunking you can do with pretty much any database these days. There are dedicated databases that are used for just storing those vectors. Pretty much every database has been added vector indexing into it as well. So Neo4j, of course, has vector search. Most relational databases have that as well. I think even MongoDB has it these days. This is common across all databases. That doesn't really make a difference for your decisions in modeling. But there are challenges as we've been identifying what's a good chunk size or getting better answers because of that chunk size. It isn't a very exact science. It's something that you need to test and evaluate along the way to figure out for your given data set that you're using, what's the right technique for chunking and what's the right size for chunking as well. Once you've done this, aside from, even if you've kind of dialed in the right chunk size, that's not even necessarily enough. Like if you look at my really awesome lorem ipsum chunks there, does anyone notice one of the challenges with this particular chunking? Here's some duplicates potentially. And 1, 2, 3. So the fourth chunk down has some very important context. says, however, never do this, ... So you might end up with a question where the answer is in chunk number 5, but if you don't have chunk number 4 saying, by the way, never do this, suddenly you're in one of those kind of MacGyver situations where you're saying, hey, cut that red cable, but first, right? You never really want to leave it that, or you certainly don't want to omit that. You want to make sure that all the information that's relevant to what people are getting to the end user is actually both correct and complete. So that one there is the tricky one, is that if you just have similarity search and you're just going to give one of those chunks, you don't have enough context to know, actually, that chunk has been negated by the chunk prior to it. So provide all of that, right? And that's the very next thing that we do in modeling this stuff in a knowledge graph, is that we say, okay, great, well, we know how to deal with that. We know that these chunks are basically a sequence of texts that we have broken up. Let's put that sequence back into the actual data model itself. So now we have the opportunity to pick windows of context. So that for any given chunk that you might provide there, and again, this gets back to like, how big is a chunk, like how big is a window as well, we at least have the opportunity for providing a window of context so that you have good matching in that first step of like what the question is to where the answer might be. Then you expand a little bit around the potential answer based on like, because you've connected things together, they can provide a window of context back to the LLM to get a better answer to the user. Along the way, we've also done one extra step here, which is not only have we connected chunks to each other in sequence, we've also connected them to the parent document. So the parent document itself might provide important context for why those chunks are there in the first place. Again, an individual chunk might be seemingly relevant for what the user asked, but you need a complete context both before and after that chunk, and also where the parent context was. So if that parent context was like, okay, this is an answer that was true 100 years ago, for instance, is it still relevant today? Maybe not. Maybe now you want to be able to, as one example. So providing full context makes a difference. And then there's the issue of explainability, which is a little bit related to, kind of the full context here, that it's not enough to just take these chunks, sequence them so you've got a complete context, connect them to the parent documents from which they've been derived. That's all super good. That doesn't always necessarily explain why this particular chunk was relevant to the user, and is it actually relevant to the user? The technique that we've seen here for people who are built itself, you start to extract basically an ontology from that text so that you can tell the user, actually, this text here is not just based on a vector similarity similar to what the user asked, but it makes sense in terms of this ontology for what the user asked, or it's similar to other things in a way that makes sense for that ontology. So if you have an ontology in your domain that makes sense, if you're going to build an ontology, you've got two things that are going to be present there. You're going to get a better answer to the user potentially, because now in addition to the text similarity, you can use the ontology for qualifying what those answers are, what the chunks are that might provide the answer. And because you have the ontology there as well, you can also let the user navigate through the ontology to verify that particular answer and also see where it came from, because you've got the parent document, and also see things that are similar based on the ontology, not just based on the similarity of the answers. So you're providing even more context for the text. Okay, this is all really good. This is improving the results from just the pure chunks with context, chunks now with also semantic context in the ontology. There's one more element that's missing here, which is that we know that there's a user at keyboard, and the user at keyboard matters so much for the relevance of the question, because users always have in their heads that they are the center of the universe, because all of us here believe that, because we all are correct in that. Each one of us are the center of the universe, right? And certainly we are when we're asking a question of Google or anything else, certainly when we're asking an LLM, if the LLM doesn't know about us and what matters to us, we're going to get less relevant answers. That becomes even more true the bigger the data set is that you're asking into, and that some of the answers might be correct, might even be most popular, but might be inappropriate for a particular user. The example I usually use here, and like if you looked at like Yelp reviews and you look at popular hamburgers near me, and you happen to be someplace where the only hamburgers available are McDonald's, okay, if you love McDonald's, then that's a great answer. If you're going to get that as the right place to get a hamburger near you, if you like McDonald's. But if you don't like McDonald's nearby, or maybe you want to go to this diner, they've got one hamburger on the menu. It's not a burger place, but you can get a burger there. So you'd like to eat local. And that's what's really important to you. So if that matters to that user, you want the user context to also matter, both geographically, in terms of their preferences, in terms of who they are and what they want. What matters to them is what is the most relevant answer. Not the most popular answer, not even the most recent answer, but what's most relevant to that user. So user context is something you incorporate as well, and you can build that into the knowledge graph. Through all of this, you get text in, find relevant text, you return some text. This is how you integrate between this alien technology and humans. Okay, that all has started to build. Probably you've noticed from just the pure text, we started to add more stuff around the pure text. What we're doing over time, each iteration through this, realizing, okay, there's a bit of a problem here. What can we add to this? We're going from the pure text to the mixed text and data situation, which opens up some even new possibilities, which is really exciting. In the mixed text and data, it's the same basic data flow. But when you're performing these queries, it's not just give me the vector embedding and actually go ahead and find out the related documents to that. We're going to use the vector embedding as an anchor for doing a graph query. And for those of you who've used Neo4j, who've learned about graph databases before, and I'll show an example of this next, a graph query ends up being basically pattern matching on data records. If you have the pure data and the data is connected in some kind of way, there's a pattern of data that emerges. And now in this context, you can use the similarity search, the vector search, as a way of anchoring that pattern search. So you've basically found a bunch of documents that might be correct. Now you're going to do some pattern matching to actually refine that set down to something that's more correct, more relevant to the user, and serve that back up to them. And I guess I alluded to this a little bit, is the context of the user matters so much. And the more you realize that that's possible, you can even realize that for that user, it's like where they are, what they care about, who else they know, what conversations they've had. So that previous conversations with the user should end up becoming part of the knowledge graph. It's part of the knowledge about that particular user, so that you can take into account their past conversations as a context for the current conversations that they're having. Because for most now and again, there are complete out of left field things that come into our conversations, even just with each other, like some idea pops into your head. Sure, that happens. But most of the time, you're dealing with a particular context that you build up over time that you care about on a daily basis. All of that can be captured in the knowledge graph as well. So you've got the general knowledge of the LLM, specific knowledge about some data set based on this RAG pattern. And then you add to that as the users actually interact, so that you know more about that particular user, not just their context, but also their previous conversations. And you can factor all of that into the answers you're providing, the context you're providing to the LLM. Okay, so it really ends up being, this interface is text plus data for complete, most relevant answers to the user at the end of the day. And now I'll take a little detour into knowledge graphs. I've been talking about knowledge graphs a little bit, or just kind of implicitly here. This is an answer from ChatGPT. When asked, ChatGPT, the answers I usually get is pretty good, actually. Not inaccurate. It didn't make much stuff up. And I think it's a very useful answer. Okay, knowledge graph is a structured way of representing information. That's totally right. Nodes and edges to depict relationships between entities. Totally good. Actually, not that different from the Wikipedia entry on this as well. Wikipedia's got the same opinion. It's, a knowledge graph is a knowledge base that uses graph structures, so nodes and edges, where the nodes are usually things, the edges are how those things are connected to each other, either through things like hierarchies or relationships, like work together, live together, those kinds of things. That ends up forming a knowledge graph. I tried to condense that into an even smaller articulation, where knowledge graph is just a data structure where information is stored. And this is the key part, I think, where it diverges a little bit, both in the nodes of a graph structure. So the records of a graph structure are mostly the things, we call those nodes. But you also store information on the edges, or the relationships between information, not just on the individual entities, but you also care about how those things are related to each other. In classical graph theory, that's why we have weighted edges, right? Like, how far is this thing away from this thing? That was the first step towards realizing that in a graph, what's most interesting is not the endpoints themselves, but how those things are connected. In a knowledge graph, that goes even beyond that, where the edges can contain whatever information is relevant to you for that particular domain. Okay, as an example, we're going to go through Stack Overflow. We've all probably used Stack Overflow at some point in our lives. And you can look at Stack Overflow as a knowledge graph, because of course it has lots of text. All data starts with the things. This is kind of the foundation stuff that anchors all data. And those things in Stack Overflow are questions, there's answers, users who have asked those questions and provided those answers. And then there's this idea of tagging for both the questions and the answers that's possible. In the properties that you can attach to those things, this is a very simple model. For the questions, they've got a title, they've got a body, they have a link to the original source out on Stack Overflow. The answers also have a body, and whether or not they've been accepted as the answer, that's also just here's a Boolean flag. Users are super simple. We just have a name as a string, and their reputation is being marked as an integer. That's their kind of reputation just on Stack Overflow. And then the tags are just simple strings as well. These things are then related to each other, connected through that a user had asked a question. The user's question has been tagged with a tag, of course. In this very, very small excerpt of the Stack Overflow graph, you end up with patterns like this, as you would expect. Everything is kind of anchored around questions. There's people who've asked those questions, and it kind of flows out from there. What's worth observing, and what I think is really kind of fun about this first step of realizing, okay, a graph is just things that are related to each other in some way, that's a knowledge graph. What emerges from that is the realization that not just one-to-one relationship that's interesting, there's actually patterns of relationships that are interesting. And with a query language like Cypher, you end up being able to basically do kind of pattern matching on data records, the way you're very lovingly being able to do pattern matching on text with regex. Like you've got regex for data records when you're dealing with Cypher, which is awesome. Because we all love regex, right? When in doubt, regex can solve pretty much anything. Okay, the data patterns that are present in this, let me try to move the flow thing again. They are, yes. So you can ignore the direction during query time if you want to. So the question was if relationships are always directed in a property graph model, which is the physical model that Neo4j has for storing things like knowledge graphs, the relationships always have a direction. It's always from something to something else. So if you've not seen Neo4j before, if you've not seen Cypher or query language before, this is a good way to start thinking about it. On the top here, you've got obviously a visualization of what a graph looks like. On the bottom here, we have text. That is, if you were typing a message to somebody else, pretty much how you might describe some of the patterns that are available on the top there. So here, there's a pattern from a user that asked a question. So it's that yellow node to the purple node through the ask relationship, parentheses for the ground bits, square brackets and arrows for the relationship part, because it's always directed right now in our query. And this is just how you think about doing the pattern matching, right? You describe it in text this way. I can click. Okay. So a couple different patterns that emerge. Obviously, there's the one-to-one patterns, the user to the question, the user to the answer. And then you can start to just extend that so that an answer answers a question that was tagged with tag. Even as I just did it there, this is one of the fun qualities of having a knowledge graph as a way of extending the knowledge of an LLM, is that knowledge graphs very naturally lend themselves to being read out loud and making sense. That is really very key for how you actually take this data and very easily map it to text that becomes sentences that you can feed to the LLM in the same way that I just read it out there, right? So this is kind of the meta graph right now, but even when you have instances of this graph, you can say, okay, this question about blah, 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 provided an answer to this question, this answer bug that ends up being what you end up providing in the prompt back to the LLM to provide an answer.
Yeah. Earlier, you have logical categories.
Yeah.
Is question and also logical category for questions?
So it's not in this instance, but it could be. So in this instance, this was just really the metagraph of like the way we're storing the questions and answers themselves, but self-stored in the graph, which would then become the ontology. So if we stored this metagraph in the graph, then yes, it would be a very tiny ontology that explains, how these things are related, how these objects are related.
So each object has a class. But there's a class. Is that right?
You can think of it that way. So that's what I guess. Actually, I don't remember if I quite have these slides or not. But so in the property graph model, we've got for every node that you create, you can apply labels to that node. So that label ends up being very easily thought about as being a class for that type. So if it's a person node is the class of that node. Okay, we know that stores things about a person. Very, very nice. The difference here is that you can add multiple labels, and there's nothing that within Neo4j enforces any kind of strict type system. So you don't have like a type hierarchy where you can have like a person and then a user is a subclass of person. You'd simply have a person who's also a user, who's maybe also an employee. You end up accumulating it, and there's no semantics implied from how you're using it then, rather than being imposed by Neo4j, if that makes sense. Okay, so the knowledge graph that you end up assembling ends up having facts about people, places, things, whatever you might have, how those things are interlinked to each other. And I love the quality of this, if you're careful about how you've crafted your knowledge graph, is it's useful both for humans to look at, because it makes sense to them. And this is one of the things that's just great, is that we've got a nice knowledge graph. You can just kind of like explore it directly as data, navigate through it as data, and it makes sense that if you understand the domain, the data usually makes sense to you. It hasn't been denormalized in kind of a weird kind of way. That same structure ends up being really great for interfacing with an LLM, because you can kind of read it out loud, provide it to the LLM once you've found a pattern that matches what a user's question might be. Give that straight to the LLM, totally great. That same data structure also can be augmented, again, augmented, to use for classic application development. If you're still building dashboards, you're still building some kind of a UI directly to the data, people can access the data directly because the domain makes sense. You can add extra information to the data, either extra relationships or extra properties, because the properties can be expanded as well. It makes sense only for the application, but maybe not for the end user. And all of that still can be packaged up so that the LLM can make sense of it as well. So you've got all these different consumers. Yeah. What makes a knowledge graph LLM friendly? Yeah, so this is what I guess perhaps implying not strongly enough here, is that what makes it an LLM friendly is because it is, as you read patterns within the graph, it is close to natural language and the structure of it as it is, right? And for an LLM, means you present to the LLM text, language, right? So it's a very easy mapping from the way the data is represented in a knowledge graph to how you would turn that into prose that you would then pass to the LLM so that it can generate an answer. So if you have a combination of pure text that is stored in a database plus data structures around that that look like language, those things combined together, concatenated together into a big context, are all very easily digestible by the LLM. Does that make sense? Do you buy that? Okay. So I'm going to give a couple of examples, and actually between the examples I give and then we'll go into a demo, maybe it'll help make some of this more real for you. But then we can also talk some more about it. So what we've been seeing from customers who are coming to us about wanting to do GenAI applications, there's a couple of different things that show up very, very commonly. Most people honestly start from just chat for their support needs. Like they already have a bunch of, kind of a knowledge base somewhere with a bunch of support articles. Exposing that through an LLM makes great sense because the LLM can take a look at that and give better answers usually to people's questions than you get from just doing what people do today, which is kind of full text search of trying to find the most relevant documents to present wholesale back to the user. You can make that much more relevant to a particular user by taking all those support answers in whatever format you've got in them, turning that into a knowledge graph, doing vector embeddings on that, and then doing the mapping, the user question to the vector embedding of the knowledge that's been taken out of the customer support stuff, providing that back to the user. Also, it turns up, being used quite a bit is even for things like policy and pricing, doing some amount of fraud detection ends up being true, and doing things like recommendations is also relevant, where recommendations, if you go beyond just kind of pure keyword searching for things, but things that are similar. So if people are looking for, fruit might map a bunch of different things because the LLM knows that in the vector space, fruit is close to apples and oranges and other things that appear as fruit. You don't have to ask for now. So I think in this particular example here, right, this is if you did have a bunch of articles that were available in a huge just knowledge base, turning that into something that is accessible to both support personnel themselves or to end users directly is incredibly valuable. That's where you're taking, usually for most enterprises, they have huge masses of really valuable information that is just stored into pure text. Turning that into something that is queryable is a huge value for most enterprises. This is the other aspect that we talked about. This is the bucket 3, where you have the existing data source that you want to be able to get people to access directly. Oh, yeah, that's a great idea. Thank you. I will boldly do so. You come here. Yeah, that's a good place to have it. Yep. No, don't do that. Yeah, this one. Oh, I appreciate you taking photos. There will be PDFs of this available. Not as good as taking a photo because you won't have me in the image. If you're trying to get me framed, right? Okay. But the PDF, I'll post that by tomorrow, actually, to make it available to you. accessing to pure data source, totally awesome. Then for lots of things that are easy to translate from pure text, from prose into a query language, this is pretty fantastic. Oh yeah, yeah.
So the vector search is actually in the local database, or
It is directly in the database, yeah. So Neo4j has native support for vector indexes. So what ends up happening is that on any node that you have, or actually if you do this relationships as well, you have the text stored as a property on that record, and then you index it. You create an embedding, and you create another field on that is the embedding. That gets backed by the index. So when you're doing the vector search, you query the index, figure out what node it belongs to, and then you get the text back that's related to it.
so the current database is acting, not database modularized.
Yeah. So in some ways, like it's kind of a natural thing to do because it's a little bit like having geospatial or any other kind of an index where you already have the data there. You literally are just adding a new index, which is a new way to get access to the source data. Yeah. So it's very natural, I think.
Furthering this point, if you're doing vector search, how about relationships? Are you looking at subsets of the graph? You do the vector search inside this thing, so back to the vector search, not just the entities, the relationship graphs.
Yeah, so that's one of the possibilities when you take this kind of middle pattern of the mixed text plus data, that you're using the vector search for kind of looking through the text that's available in the records, whether they're stored in nodes or in relationships. That ends up being the pattern of sort of the anchoring point for a pattern search that you might do. So you have a normal graph data query that you then have also some text associated with. So you do the vector similarity search for that part of it, but that ends up being part of the pattern you're then going to match to get a complete answer, which ends up then being this mix of the pure text plus the data all in one query. So generally what we end up seeing is that like if you have and I guess right to your point, like if it's a well-structured knowledge graph, you end up refining the set of information you get out of the vector search. So the vector search, if you have a lot of documents, you'll get a lot of duplication, a lot of things that are irrelevant, and the graph pattern matching usually ends up refining that or reducing the answer set. So this is the pure data with the text querying. And then the mix, this is just another example of that really. If you, in this particular example, if you had a bunch of RFPs, and this goes back to actually the duplication point where in, many federal situations where there's an emphasis on efficiency and you don't want to have, multiple requests and like procurement, processes going on for what ends up being the same thing. That's hard to see as a human. It's hard to actually realize that like 3 different departments are asking for the same thing, unless you actually take the time to read all this stuff and happen to have remembered that somebody's asked for the same thing. It doesn't show up in most systems very easily. But if you do vector embeddings on all of those things, all of these similar RFPs, when a new RFP comes in, they'll end up being in the same, very nearby each other in the vector space. You can actually bubble that back up to the users so that people during the procurement process can realize actually the thing you're asking for, somebody else has already asked for it. We can double the numbers, whatever it might be, to actually improve the efficiency of the procurement process. I guess that was my last example for today. Soham is going to come up in just a minute here and then show us a live example of how to actually use Neo4j. I think that's based on SEC filing data, right? Which you can explain, which is pretty awesome. The big takeaway for me from this talk is everything's got to be text-based if you want to deal with an LLM. Either you've got text, and that's pretty great, that's an easy pattern, or you've got to create text because you don't have text, so you've got to translate from text into a query language or something like that. Results still have to come back into text, so you can provide that to the LLM to actually get any kind of a prose response to the end user. But text is the basis of doing everything, and RAG is the way to go about that. For a live demonstration, my good friend Soham is going to come up and show us how to do this with Neo4j, a nice demo that we've set up. And we're also going to have a small technical break while we swap audio and those kinds of things. Let me turn this off for a second.
You can work with the LLM.
I'm sorry?
LLM.
No. Yeah, you can integrate with any LLM.
Yeah, right. So it should just be turning that switch on.
Okay.
So one of those technologies I mentioned earlier on, your question was called LangChain. One thing that LangChain does is that for most LLMs, you don't have to talk directly to the LLM. Off the LangChain, they kind of abstract away some of the interfaces, so the pattern is pretty much the same. Hey, here's some text. Giving the continuation of the text is the fundamental thing you're doing. The other fundamental operation is I got the text. Could you create an embedding for this? And really two interfaces is pretty much fundamental across all LLMs with regulatory providers.
Can you folks hear me? Okay. All right. I promise no more than 3 slides. Okay. Thank you, ABK. Okay. So along with the retrieval augmented generation pattern that Andreas was talking about, grounding is a mechanism where you basically interface with your source of truth, which in this case is a knowledge graph, which in this case is Neo4j. I realize I should be standing here.
There's a note over the title, maybe X out.
Oh, okay. Yeah. Why ground your LLM? So knowledge graphs will serve as a source of truth for your application that's interfacing large language models and your source of truth. Retrieval augmented generation is a mechanism, and grounding is a sub-processing. So just as an example, let's assume an insurance company analyst asks a question, what was the impact of Hurricane Calvin that happened in Hawaii last year? A regular LLM, or really any language model which is not specific to your business case or is grounded with your enterprise dataset, will give you a generic answer saying, okay, Hurricane Calvin caused minor flooding, such and such property was destroyed, all these losses happened, and everything. But in the context of insurance company, the generic answer was not complete. So in this case, knowledge graphs will help you complete that answer by adding more context, like Andreas mentioned, and say, okay, 50 policyholders filed for property damage due to Hurricane Calvin. And then you can drill down in your knowledge graph. Okay, so who are these 50 policyholders? What are all they insured for? And so and so, if you can imagine a graph like Andreas showed. Or just and that's how we ensure for more accurate, relevant, and complete responses, so that we don't miss out on the context for who's asking. Andreas had a really good slide there where the person asking the question is at the center of it. If the answers are not relevant to the person who's asking those questions, the answers kind of become kind of useless. I'm going to try to escape out of my presentation here. Okay, perfect. So let's dive into the fun part, the demo. Hoping it would refresh. The data I have is the SEC 10K filing dataset. It's essentially a document for every company with their business processes, with the products they have. And what we have done is we have chunked and ingested those documents as a knowledge graph. Yeah, there is a simple dashboard. It's a Streamlit application. I'll be sharing repositories, which is the link right next to it. We'll go a little bit into the code, not too much, because we could be here all night. And what we have done is we have ingested those documents and created a data model of it, a graph data model of it. We'll go into that as well. And that tells us, okay, who are the managers who own these companies, what documents are associated with them, and where are they based out of. So let's go into performing retrieval augmented generation with Cypher. Cypher is Neo4j's query language. OpenCypher is the open source language used by almost all the graph databases out there. And what we'll do is we'll just ask a question here. One of my favorite questions is asking the LLM, which manager owns FANG stocks? So we all know FANG is Facebook, Amazon, Apple, Netflix, and Google. But knowledge graph does not really know what FANG actually means, right? FANG is a generic term. But in this case, the LLM does know what a FANG is because it's out there, right? It's everywhere on the internet what FANG means. So LLM is going to combine its knowledge of what FANG means and the knowledge in Neo4j and give us the answer. You can also see the Cypher query here, which gets generated at the back end. It's saying, okay, tell me all the manager who owns a company where name of this issuer in the 10K filing contains Facebook, Amazon, Apple, Netflix, or Google, and give me those manager names. So this is just a really simple example of how LLMs can help augment graphs and the other way around. Because imagine asking this question just to Bard or Open or ChatGPT or anything else. They won't know, or they would, but it's combining all the knowledge out there on the World Wide Web, which could be incomplete. Yes, sir.
For the data schema that we have within the graph database, it's that we don't have like the name of the issuer, but it's the particular names. The LLM automatically adjusts the Cypher query based on like the particular names in AAPL.
Okay, so the question is, will the LLM automatically adjust if the property names or if the data elements are differently named perhaps? Yes, it will, because at the back end, what the LLM is doing is it is taking the question, breaking it into its constituents, right? And then doing the same for Cypher query. So while generating this, the retrieval part that's happening, it's really looking for all the data points in there which point to something from this FANG, right? FANG is these 5 companies that's coming from LLM. And then, okay, it's going to search for these names anywhere in the database. It's say, okay, could be c.ticker name, could be c.just name, right? One hot tip here is you could also do few shot learning in your prompt template and add examples. So let's say name of issuer is the property that I know of in my database. If it's ticker name, let's say, you could write a few short learning example in your prompt saying, okay, if such type of questions arise, you know you have to do c.ticker name and not c.blah blah blah. Does that answer your question?
Yeah, partially. I can adjust my prompt to any way that Neo4j can is with the handling, the prompt handling.
Yes. Yes, okay, so the question is, can Neo4j handle the communication between large language model and actually where the data is sitting, right? So yes, Neo4j and through LangChain that Andreas shared the slide, right? LangChain is the central component where you can specify which model to use. In my example, I'm using AWS Bedrock and the model is Anthropic Cloud. So you can specify which model to use. And in that, you can define your schema definition. So the data model we have is passed into this object, in this function as an object. And that's how I guess that's how that LangChain object knows what all is there in the database. Okay, name of the issuer is one of the properties, and so on. And I'll show you the code in a couple of minutes. Yes.
Can you just click on Q&A? You might have some questions online.
Okay.
And for folks in the room, feel free to use a microphone that somebody sends you. So your voice is more audible to put on as well.
All right, the first question is, the augmented text is still taking up space in the context window, correct? Yes, it will, right? Yes, it will, because most of the enterprise LLMs out there are based on input and output tokens. So the augmented text or augmented piece will always take up space in the context window. What impact does temperature have on this process? I think knowledge graphs will help aid in that process because one example, I was talking to a customer last week, and traditional LLMs have a knowledge cutoff, right? So they are not really up to date as to what happened yesterday. But if your enterprise data, let's say there's a Kafka queue or there's a Spark job writing to your knowledge graph, that means your enterprise data is always up to date. And these LLMs are actually connected to your enterprise data, enterprise knowledge graph in Neo4j through this LangChain function. And since your knowledge graph is always up to date, your answers are always up to date. If you remove the enterprise knowledge graph piece, you're left with just the knowledge that LLMs have. And Jim, we can go into this deeper in perhaps a follow-up conversation.
What exactly is it?
Yep.
Single answer.
Mhm. Yeah, no, that's a good question. So was that?
Can you repeat the question?
Yes. The question was, what is the knowledge graph piece of this? Because let's say it's a relational database, you can do foreign key tables and get the same answer out of it, right? How does knowledge graph help? So in my mind, and when I talk to my customers, it goes back to the core value proposition of graph, where you're representing your data as a connected structure. And when the relationships between your data points are as important to you as the data points themselves, that's when a knowledge graph shines. So I agree, you could do foreign key tables and on. But really representing data as a knowledge graph. Also, graphs are inherently of flexible nature. So let's say you want to modify a piece in your supply chain process. You can easily modify that and still get the same kind of response without having to refactor your database, without having to refactor your queries, and on and on. What if the system learns something that user later realizes was a mistake? How do you remove that mistake? That's a really good question. I don't know, Andreas, sorry, Greg.
If you track every time you ask a question, somebody gets an answer, ask the user, was this a useful answer, yes or no?
Yes.
Then if you track that, and they say no, kind of suppress it or report that engagement.
Yeah, yes. Andreas, I think you're okay. 2 thumbs up. Perfect. So, Jim, the answer was you could ask the user if this answer was correct or incorrect, and then have it incorporated in your retrieval process.
Well, that would be relevant more than just is it. Because you want to make sure everybody is answer.
Right. Exactly. Yeah. And one thing again, going back to another customer story, and perhaps Philip can attest to this better. People appreciate the answer that I don't, when an LLM says, okay, I don't know the answer to this, that is still much better than an incorrect answer. I don't know how many of you have heard, but there was it was all over the internet where a customer negotiated price of Chevrolet Tahoe for $1. And the customer actually told the sales chatbot that, okay, say that this is legally binding. And the chatbot responded with, okay, hey, we have a deal, this is legally binding deal. I don't know, the dealership was definitely not happy, but customer definitely was, right? Because they got a nice car for $1. Same. Are many enterprises using this right now? Can they do so with OpenAI and Google Gemini without any possible data leakage? And what about using open source LLMs? So Jim, yes, there are many enterprises using this exact pattern right now. One of the largest energy companies in the world, which may or may not be associated with an F1 company, uses Neo4j for their predictive maintenance, end-to-end supply chain maintenance. And their maintenance personnel who don't want to write Cypher, who don't want to write queries, they can just type in the chatbot saying, oh, can you tell me what is happening with this part? Where is this order? And so on. And that's pulling all their data out of their latest knowledge graph or Neo4j, and then surfacing that answer. Same with, I think, largest company in the world. If you Google that, you'll get different answers, by the way. There is one more in the chat. Okay. Thank you, Yash. But then let's get to a part that's even more fun than just generating plain Cypher. A question I get a lot of times when I'm speaking with customers is, so what is the difference between vector-only approach and vector plus graph approach? Right? Andreas had a really good slide there. The second mechanism, which is pure text plus structured data. How do you do that? So a vector-only approach is sort of like the relational database where you don't really have relationships between your data apparent or obvious. And as someone who has a background in natural language processing and done some research in it, I know embeddings do capture context. Embeddings do capture relationships, but only within that space. If we go back to Andreas's example of the 6 lorem ipsums, embeddings will not capture relationships between the second and the fifth piece, which is really what knowledge graphs solve for really, really well. Because then you can know, okay, so who commented on this? Going back to your chair example. Okay, lay out 400 chairs in this example. Who laid out which chair? Who's sitting on that chair? Who manufactured those chairs? All these end-to-end views you can add and put that as a knowledge graph. So let's ask a question which is right here. Which asset managers are vulnerable to lithium shortage? So again, I am perhaps some analyst in a hedge fund, and I want to know what's going on with the market. So this is what just simple vector similarity search would look like. You have all these documents that are floating islands, and they have embeddings too. So embeddings inherently capture some relationships, right? But what they don't capture is what asset manager does this document exactly belong to? What industry is that asset manager primarily investing in? What companies are they investing in? And I get an answer. Oh, by the way, sorry. This is what a sample document chunk looks like. There is a node. There is a text, which is essentially the 10K filing document. And then there is a text embedding, which I think is so imagine these documents floating here on their own, and you are calculating vector similarity between those using Neo4j vector search index. And again, reiterating, it is only taking those documents into account. It is not taking into account which relationships is that document accessing. So if you do just a simple similarity search on those document text, on those embeddings, it's going to give you a quick summary of, okay, there are companies who have battery technology, and because of lithium shortage, battery technology companies are going to be affected. For example, Tesla or something like that. And then there is also some note here talking about credit markets and the company's ability to access liquidity because of lithium shortage and so on. But now, before we look at the answer here, if we have a knowledge graph and we are combining the second approach that Andreas mentioned, if we are combining this knowledge graph with vector search, with vector indexes, this is what you're accessing. Not an island node, but you are accessing a document that belongs to a company. The manager who owns company, manager is essentially a hedge fund, and then company is Microsoft, Apple, Intel, all of this. And then manager and their locations. So you are accessing complete context of what was asked, right? We asked which asset manager are vulnerable to lithium shortage. So the query is going to start on managers who own companies who have documents. That's the pattern we are traversing. And then at the document level, it's going to look at similarities between such companies who have these 10K filings that mention lithium shortage, and then the managers who are going to be impacted by it. Just as an example of how the data would look like, cyber management owns Coinbase Global, has this from 10K item, and has address in New York. And you get an actual answer. You get name of the managers who are going to be affected instead of just some summary. And it says that, okay, this context indicates that Stanley Black & Decker uses lithium batteries in their production. And with the increase in demand, there could be supply chain constraints, and this could negatively impact Stanley and Decker. Because of this, the asset managers investing in Stanley and Decker are going to be suffering. That means, going back to our modern view, Stanley Black & Decker is a company, and all the asset managers who own Stanley Black & Decker are going to be suffering because of the lithium shortage.
So did the LLM figure out that it needed to make that particular two-step query?
Yes, it did. Just like in the previous, on the previous screen, just like it figured, I need to traverse from manager to company. Okay, yeah, I'll probably be done before that. So yes, the question was, did LLM automatically figure out that it needed to do this two-hop traversal? The answer is yes. LLM automatically as in using its knowledge and the knowledge in Neo4j, it figured out, okay, document is two hops away from manager. So I need to jump 2 hops before I get to the document, and then before I access that vector property, before I compare that vector property. Yes, sir.
Now, Neo4j, did you fine tune it or you just did this on?
That is an excellent question, which thank you for taking it for that. The question was, how does it know Neo4j? Well, first of all, it was trained on World Wide Web, and there are so many examples of cipher queries out there. Being one of the largest, or being the largest graph community in the world, there are a lot of cipher queries out there in open source, which are also helpful. We also have our own project of training these LLMs on cipher. And also we have a few short learning examples, which I'm about to show now. This is the GitHub repository that I have used for this example. So if you run through this exact GitHub repository, you'll get this exact Streamlit app. It says Neo4j Generative AI AWS, but we have the exact same thing for Google Cloud and Azure, cloud agnostic. And getting to the part where the question was, how does it know Neo4j? So in this notebook, we won't go into it one by one, but let's just jump to the part where, let's just jump to the part where I'm initializing Bedrock. So from LangChain, which is again the central piece, remember, from LangChain, I'm initializing this Bedrock model. I'm saying, okay, within Bedrock, I want to use Anthropic, setting the temperature, setting max tokens and whatnot. And then comes the grounding part where you're actually doing retrieval augmented generation. So there was a question from someone about how do you fine tune it, or how do you make sure that the proper keyword, proper property is accessed in Neo4j? You can define a prompt template, and which is really the key to getting it correct. So we have here some really basic examples of what kind of questions would a hedge fund manager or analyst ask, the cipher queries pertaining to that. And it's really good to write like 10, 15 queries and pass them as a prompt template. So what we are going to do, by the way, the database, this Neo4j is hosted on Neo4j Aura, which is our fully managed service. I have a link up here. I'll show in a moment. And then once you have that, we are initializing the chain here, which is incorporating the bedrock model, which is incorporating the graph, and the cipher prompt, which we have written up above here. So this chain is what is going to carry the workload from step 1, where a user asks the question, all the way to step 5, maybe 6, step 6, where the answer was populated on the screen. And then there is a very nice piece of code which a bunch of my customers have liked to use for their own chatbots. You can initialize and use this code for your own chatbot applications for proof of concepts or anything really. And of course, we'll share these links in the meetup section. Going back to where it was hosted, it's hosted in our fully managed service Neo4j Aura. You don't need to spend cycles setting up any database really, so you can just click and deploy. It's free to start, available on all clouds through the marketplace. And basically, you can perform this whole exercise for free. Of course, there is a cost to Bedrock, but minus that. One amazing resource to get started with Neo4j and LLMs in general, hands down, is GraphAcademy. So GraphAcademy is our free online resource to get yourself trained on all things Neo4j, starting from Cypher, graph data modeling, graph data science, which probably will require a whole different meetup. But we have a section on Neo4j and LLMs. So just the fundamentals of what RAG can do, what grounding can do for you, and then building a chatbot using Python. So the repository that we have, similar one, maybe a different database, maybe a different data set in the database. And then there are a few others coming out using TypeScript, and third one is my personal favorite, constructing a knowledge graph. So remember, at the start of my demo, I said we have extracted these entities in the SEC 10K document using LLMs. So you can use LLMs to actually extract entities and relationships out of these documents and have them as a knowledge graph. That is a part of this repository. Maybe step 2, no, step 1. And that is really powerful because that is going to, yeah, there we go, parsing data. That is really going to accelerate time to value and time to first deployment by a lot. Because consider, okay, you don't have to write loading scripts anymore. You don't have to interface with or use any other external Python libraries anymore. You can ask the LLM to just parse, right? The only things you need to do really is define what those things mean. So, okay, in that SEC 10K filing document, there are so many things, but what matter to me is the manager name, is the company name, is calendar or quarter report, share value, number of shares, investment discretion, and all that. And then you can ask LLMs to parse it, and you can, of course, refer this code. Cool. I don't want to go too much, or yeah, I don't want to go into every line of code, but essentially you can use LLMs to parse data out of free text, put it as a graph, combine with your enterprise data sources. Yes. That's a good question. Through your first thing is through your prompt template, and the other thing is you can also add Cypher, which so you can also add Cypher queries as your prompt. So as you go, you can say, okay, take only managers. Don't take managers under cars, for example. I don't care about the cars that these managers own. Just take managers. And I think it's also an iterative process. So I mentioned flexibility, right? That's the kind of flexibility you get with knowledge graphs and Neo4j, where you can quickly iterate and say, okay, I don't care about the cars that these managers drive, but it has been ingested somewhere. Due to its flexible nature, of course, you can enforce constraints, but due to its flexible nature, you can say, okay, I don't want cars, remove car as a node, remove car name as a property, and make it more iterative.
Yeah, I was thinking about the example that you gave.
Mhm. 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 Well, the question was,
Yeah, and the portfolio of investment. I tried things, yeah, and 50% of my stocks are basically, like the prices up. My portfolio only 5%. This is also out of the graph. This was not ours. It was only like, yes.
I think Greg, you have raised your hand. Are you answering the question or do you want to?
That's very nice.
Okay, so the question back there was the prompt was not accurately answered. It just said these managers are impacted. It did not tell us what percentage impact was there and so on, right? Uh, that's a good point. But the question we asked was which asset managers are vulnerable. We could go into specifics. I don't know if that data is there in the in Form 13 or in the specific database, but the question we asked was which managers are vulnerable. So essentially, the output was going to be list of names. If we or the question could have been better phrased, and I think that's a general challenge with LLMs that I have seen, is that you need to ask specific questions in order to get specific answers. If we ask, okay, tell me Citigroup, tell me what loss is Citigroup going to face because of lithium shortage, that might have given us answers. And I don't think there are financial details in here. But that could have maybe given us some impact answer. But since the question was about, okay, give me a list of managers, we got a list of managers who will be impacted if a company faces lithium shortage. Right.
Question, anytime you have a large structure, data structure,
Mhm.
then people figure out what field name, how do I spell zip code, zip underscore code, zip without the word code. So there's all these different ways. So if you're generating a part,
Mhm.
or has to know the syntax.
Yes.
Of the fields, tables,
Mhm.
if there are some kind of language chain step that does a lookup and you think it's natural language, it might have to send it to some database field, then we get the exact database field name. Because you don't want to define it prompt engineering, because then every time you have a text, then you have to redefine the entire prompt definition. That eats up really fast.
Right. Yeah, that's a good question. So the question was, if there is ambiguity in property names, let's say there is zip code, there is zip underscore code, or first name, first underscore name, something like that. Will LLM be able to figure out on its own which property to access? Right. That was the question.
What's the spelling of the particular prompt?
Mhm.
That structured data.
Yeah.
Neo4j.
Yeah, so that's a good point. I have seen both. Sometimes it does figure out. It also kind of depends on how you fine tune your LLM, which in this case is Anthropic. So we would need to go into some hyperparameters of Anthropic and maybe set tolerance levels and all that. Set temperature. There was a question about temperature. But if we talk about the Neo4j part of it, in LangChain, there is a part um, where you pass Neo4j schema to the template. So this is where you are basically extracting the schema and then passing it down here. Gosh, where did it go? Yeah, I think that was the one. So you're telling the LLM to grab schema, which is essentially an object, a large object, and within that object is all these. So let's say it's spelled zip underscore code on 100,000 nodes, and it's spelled as zip code on 50 million nodes. But there are still both spellings. In the schema, both of those are going to be extracted. So you still have both, and if someone asks for zip code, it still knows that there are two objects that might need to be accessed.
I think we have to stop now.
Okay. Okay, yeah, we can set up follow-up conversations through email, call, whatever, whichever works.
Okay, if people have questions, but you have to be migrated out of your body. I need to see everybody out. If there's something left over, we'll have to talk about anything else you want to say.
Hello, just want a quick show of hands. Are you trying to see any of the decisions of hit dropper? Is there the drop again? Okay, so mostly it was Jupyter. Yeah. Okay.
And also, thank you for actually, you've already, nice.
We also have Philip in the room. I don't mean to put you on spot, but he leads our technology for the whole company. If you have really hard questions, go to him. Should I think?